let's find our seat and get ready for our next session, second session. So we have all the presenters and authors have time to show their work, and you have some of the cookies, and we also have something else. Statistical physics for babies. Nice, I want a copy. So we have two papers in this session. The first session is going to be, the discussant is Andrew Goodman-Bacon. He will be presenting the paper, Counting the Fires in Healthcare, a design-based model of an experiment, case reveal evidence against monotonicity, and followed by presenter Stephen, who will be present negative control falsification test for instrumental variable designs. So thank you so much for agreeing to discussing this paper. You have 30 minutes. I will
let's try it. Okay, so I'm Andrew Goodman-Bacon. I am an opportunity supervision institute at the Minneapolis Fed. And this was a really fun paper to read, and I think that I think the best job that I can do in this role is to like get everybody on the same page about the question that's being asked and the way it's being answered, because it's a very different kind of methodological paper than a lot of things. I mean, I'm used to reading or producing papers that are interested in some causal parameter and define a research design, talk about the assumptions and estimate the parameter, and there's some inference stuff. And it's not, this one's not exactly like that, but it's very fun in a deeper philosophical way. And it's tackling some of the questions that nevertheless have like incredibly important meaning for the things we do with the data sets we get. So I'm going to use the already excellent and very well thought out slides that put together for this paper, and hopefully get us with a common understanding of what's going on, and then I think this will be one that's like very good for discussion, because again, there's lots of complicated stuff going on from my point of view, but there's also been a ton of work put into this already to communicate those ideas in an intuitive and a clear way. So the setup that you should have in mind for the simple case that illustrates the core ideas of the paper is that you would like to get pregnant women to take up a desired health behavior. Okay, and the example here would be to quit smoking. And you want to do it with a financial intervention. And so you're just trying to figure out how to use money to incentivize this good, positive health behavior. I need to be way closer to the mic. Sorry about that. But you might worry that some people are a little salty about this, and they resent being paid to do such a thing. And so, in fact, they might start smoking or keep smoking and say that they've offered money, because how dare you just try to manipulate them in this way. So maybe some people behave that way, and that would be really troublesome, because we don't want pregnant women to be smoking. And if there's a subpopulation like this, we need to know this in order to properly allocate efforts in the real world, not even just in the experiment, about how to encourage such a thing. So you're going to try to figure out, but just without thinking about that detail, you just in general want to know, can we use money to get people to do more of a good thing? So you're going to do a randomized experiment, and maybe we're in, I would think of this like, some medical trials are like this, but I even read a lot of like medical history, and sometimes people are doing RCTs on like 6 people. So maybe that's the world that you're in. You're going to have 6 people, and you will flip a coin and put 3 in the treatment and 3 in the control. And what you observe when you do that is that 2 of the women that you've put in the intervention and paid do report that they stopped smoking, and only 1 of the pregnant women in the control group receiving no financial incentives reports at any time that she has quit smoking. Okay, you know, because it's an experiment, that absent any sample size issues, this is a good estimate of an average treatment effect of the money on smoking. So you conclude this little small experiment and you say financial incentives increase the probability that women will stop smoking from 1/3 to 2/3. But that is only, in an experiment, a statement about the two marginal distributions of potential outcomes. So you know that if everybody were to be given financial incentives, 2/3 of them would stop smoking. And if nobody were to be given financial incentives, 1/3 of them would stop smoking. But that's not necessarily the whole story, because it could be the case that some of the women who kept smoking, the one woman who kept smoking in the treatment group, maybe she's this sort of backfired person. And we'll wind up talking about the terminology to describe this in a second. But right now, just think of like she might be a contrarian who saw the money offer for money and just said, no, I'm going to keep on smoking. But you don't know. You can't tell that from just the pure experimental treatment mean and control mean. But in a medical context, it's incredibly important information to know. And I'm very, I guess, happy to be standing here at Michigan again talking about this, because a version of this question is something that used to come up when I was talking to my advisor, John DiNardo, years ago. One of his major criticisms of average treatment effects as an interesting causal parameter was in a situation just like this. Suppose there's a medical intervention that kills half of us if we were to receive the treatment, but it saves half of our lives. The 8 might very well be 0, but it's absolutely not accurate to say that this is an ineffective medical treatment. It's extremely effective, just in opposite directions for you and you. And so this more subtle question, it's generally not answerable in the way we think about RCTs, is what the paper is interested in. And the reason that statistical physics for babies is here is because it's going to be the very helpful bridge in terms of communication for trying to understand how we can use the design-based structure of an experiment to try and infer the presence of these people for whom treatment backfires. And we just want to know, can we learn anything more from the experimental data about this type of person? And this is the crux of the paper. I think in a healthcare context with extremely heterogeneous treatment effects in terms of sign even, it's obviously an extremely important point. And I want to even add one interpretation on top of this, which fits very well with our economics language. We'll describe this, we'll talk about this in a lot of ways using like causal experimental type language. We'll use some IV type language, but I think in economics, this is also very, very, very related to the importance of allocative efficiency. And so if we can understand that we are in a situation, if we can empirically understand we're in a situation with heterogeneity in the sign of the treatment effect, that suggests the allocation is absolutely crucial. And in fact, this is really related to the paper we just heard. If we know we can shuffle these patients around, we can keep the cost, or we can keep the capacity constant and do way, way better. And that's kind of an idea that's at the core of thinking through the questions that are being asked here. It's not just what's the average effect, which we can learn well from an experiment. It's where does that average effect come from, which is a very deep and important question if we want to then think through optimizing and allocating treatments. So let's talk about how this is set up. Now, we're going to go into some, you read this paper, you'll be very entertained and interested, and you'll learn a lot. But I want to just pitch that there's like 2 parallel ways to think about some of the terminology. So the examples that I was just giving you, pregnant women taking up smoking, or a medical treatment saving my life but killing you, those are like treatment effects on outcomes. That's what I would think of. So that's why we use the word like backfire or harm. But we do have another kind of parallel set of terms in economics that reflect this notion, and it's more about IV first stage language. So we also know what always taker, never taker, complier, and defier mean. And that's also a perfectly interesting way to interpret everything in the paper. And the paper does go that direction and uses these 4 terms: always taker, never taker, complier, and defier. But I just want to say we could have a whole version of this that talks about the methods of the paper in that IV first stage compliance context, where sometimes the instrument makes me not comply, sometimes it makes you comply. Some of us always do it, some of us never do it. And that would have a whole IV interpretation on its own. But then there's an interpretation where comply, backfire, etc., refers to the actual, say, like a binary outcome of interest: quit smoking or not quit smoking. die after surgery or don't die after surgery, etc. So when we go, just keep in mind that there's like a treatment effect heterogeneity version, which is, to me, like a very motivating example for why understanding these questions is important. But almost like an extra thing on top of it, you could also just be having this whole conversation in the context of IV first stage language. Okay, so now imagine we're going to go back to our 6 people, and now we'll get in a little bit to the meat of what's the question being asked, and by what methods are we going to try to answer that question and in what way. So on the left side of this experiment is the left box is going to represent being put in the treatment group that gets money. Okay, so everything you're going to see on these really nice slides, the left side is like getting treated, and the right side of all objects on the slide is not getting treated. Okay, so here we just say, okay, I could take people and put them in the left box, that's the treated group who gets money. I could put people in the right box, that's the control group who doesn't get money. So we're going to use this left-right kind of dichotomy to think about types of people who fall in these different categories. We could call them always takers, never takers, compliers, defiers. We could call them always respond to the treatment, always like good outcome, always bad outcome, respond to the treatment positively, respond to the treatment negatively. We could call them that, but we're going to represent them. People are circles, and they're what happens to them in treatment versus control. Their 2 potential outcomes are the left side and the right side of their circle. So suppose we took these 3 people and we put them in the treatment group. That's just one way that the randomization could have occurred. We would have flipped a coin, the heads would have gone to the left, and this is one way for those 6 coin flips to go. And when we do that, they are now in the treatment group. So what we see for them for real in the data is the left side of their circle. And so orange means take up. In the IV interpretation here, that would mean I comply with the instrument and I do the treatment. In the heterogeneous treatment effect, that means I got the money and I did the good outcome. So, but it just means responding, I would say, positively to being in treatment group. And in this particular data that we see for this experiment that we went through at the beginning, 2 people in the treatment group sort of did take up, responded positively, quit smoking, whatever. 1 person didn't. That was the 2/3 number. But what we, of course, don't see for them is their counterfactual. We don't see what would have happened had a different randomization put them on the right-hand side. But, of course, we have the control group, and that is what the randomized experiment is going to help us do, fill in information about that counterfactual. And this is where we would see, given the experiment we described, 1 person quitting smoking in the control group and 2 women not quitting smoking. Okay? But of course, their treated outcome is not observed. So the question is not what's the average treatment effect of this intervention. That is already answered by the experiment. The question is what potential outcomes, what joint distribution of potential outcomes could possibly have generated this? And it's the jump from like the marginal statistics about the treated potential outcomes and control potential outcomes. That gives us 8s and stuff. It's the jump from that to asking questions about this joint distribution. That's where we start to allow this notion of like understanding defiers, understanding backfiring treatments to enter in. That stuff is all about joint distributions of potential outcomes. So this is where you can start to see the nature of the question that's being asked. It's saying we already know what to do with an experiment to infer an 8, but can we do more? And that's an exciting question to ask, because especially, I think my sense is that would have been a much harder question to motivate, I would say, outside of healthcare applications. I think medical and healthcare applications are an extremely important place to think through this, because we all know that the stakes are very, very large. So let's just imagine what answers to that question even could possibly be. So potential answers to this question of what is the joint distribution of potential outcomes are guesses about what the full circles in the experimental sample could possibly look like. So one guess could be, suppose that the 6 women that we have here, 2 of them are always takers, 2 of them are compliers, 2 of them are never takers. That's just, it could be true. This is the answer that you would get if you wanted to impose monotonicity, right? So imposing monotonicity means no defiers. Treatment only weakly pushes you in one direction, and this would satisfy such a thing. Also notice that this is a guess about the population that preserves the marginal distributions that you see here. So if this were really the population and we had done the treatment to everybody, 2/3 of them would have quit smoking. If we had instead not done the experiment at all and interviewed these people, 1/3 of them would have quit smoking. So you can kind of see how this guess about what's true at the population level matches the thing that we really did see in the experiment. But it's not the only thing. It's not the only population that's consistent with the experimental data that we saw. You could say, well, what about this? What if there was one defier? And now if you want to preserve those marginal distributions, you have to make some other changes. So but this is one that would also do it. I would say this is another guess. You could just, it's nothing logically wrong with also guessing that this is the population things came from. You're giving up monotonicity, but it's not totally off the table. And then here's another one. What if there were instead 4 compliers and 2 defiers? Okay, so nobody is always going to quit smoking. Nobody is never going to quit smoking. Another guess could be there's 2 kind of contrarians and 3 rule followers, let's say. And that would also be consistent with the experimental data. So the method of this paper is asking, we know what we see in the experiment. We know that it's a very consequential question. What kind of population, what kind of joint distribution of potential outcomes generated that information? And how can we make a guess about which of, I just gave you 3 options that could have been the answer. How can we adjudicate between those? It turns out that the method of this paper in this specific example would say that this is the most likely population to have generated our experimental data. So not the monotonicity population, but one in fact with 2 defiers. And so now the meat of the paper is to say, well, how do you arrive at this conclusion? And I want to emphasize this is a key place where the methods of the paper become different than what I'm used to, at least. This is not a target or research question that's like, I would like to estimate an effect, and I'm going to show you a research design to do it. This is now where the paper starts to use tools from statistical decision theory to reframe its goal from estimation and inference in some sense to, I want to empirically justify the best choice, which population is the most likely one. And that's a little bit of a different goal than a typical kind of estimation and inference goal. But I think you can also see when you link this kind of deeper intellectual content to like applications, why that would be such an important and basically actionable thing to be saying out of a piece of research. Okay, so why would that be true? Let's look at what we do for sure get from an experiment in terms of thinking through these populations. And one thing we get for sure is just the data we see. So we know that this is the result of the experiment, 2/3 quitting smoking in the treatment group, 1/3 in the control. We also get a known distribution of potential treatment allocations. So the randomization means every one of these distributions could have been true. So let me walk you through what a picture like this looks like, because it's pretty key to the content of the paper. What you see on the left is one possible guess for what the joint distribution of potential outcomes looks like. Okay, so that's the monotonicity guess. We talked about that already. And what you see in every little gray kind of vertical thing is one possible treatment allocation that could have happened with the coin flip. So like on the first one right here, this is an allocation where the coin flip put 2 always takers and 1 complier in the treatment group, and 1 complier and 2 never takers in the control. That's just one of the ways the coin could have gone, and if the coin went that way, we would have gotten 100% quitting in the treatment group and 0% quitting in the control. So we didn't get that. So probably that randomization with this population is not what actually happened. That's not consistent with the data we saw. Again, you go over on the boxes, they're just different randomizations that could have happened, could have happened, could have happened. And so the interesting question for thinking through, is this a likely reality to have generated our data, is how many of the randomizations are actually consistent with the data we saw. So what you can see by just, counting that up in this nice little small sample case is that there are 8 possible ways to have flipped the coin with that population to have gotten 2/3, 1/3. And you can even think through like, why is that true? You need to have a randomization that like actually gives the results of the experiment. So things that put all of the always takers and a complier in one group aren't going to work that well. Things that put all of the never takers in one of the compliers or all the compliers in one group, they're not going to work that well. It turns out that a feature of randomizations that are very common here or that work here are that they're going to need to have like balance between the treatment and control within each type, right? So the ones that are going to work, everyone from this population that actually reproduces the data has one always taker in the control, in the treatment, one always taker in the control, one never taker in the treatment, one never taker in the control, one complier in the treatment, one complier in the control. Now, the intuition for why that's a feature of likely randomizations is that randomization tends to balance stuff. That's what it's for. And so this is just another way to say that randomization is going to tend to balance things. In this case, the thing that is being balanced is types across treatment and control group. That's going to be a very important feature for sort of going backwards and saying, okay, randomization is usually going to balance things. Therefore, which populations are likely to generate the data? They're going to turn out to be populations that are balancing is sort of possible. That's one way to think through that. So let's look at another option, right? So we sort of already saw, we counted up 8 out of the possible 20 randomizations in this experiment could have generated the data, so that's a likely debate over 20. But here's now, then the next question is like, okay, but what about another population? How likely is a different population? Because that's the fundamental question that we're asking. So now let's go to the one with 1 defier, 1 always taker, and 3 compliers. So just to preview what this is going to turn out to be, this is going to turn out to be less likely. If you followed this balancing logic, it's less likely because there's only 1 always taker. That always taker is going to have to be in one group or the other, and so always takers won't be balanced, and experiments are really good at balancing things. Same thing for the defier, same thing for the never taker. And you can see it just physically in this setup because only 1, 2, 3, 4, 5, 6 randomizations from this population actually reproduce the experimental result. And so here, when we're going through and we're counting up these randomizations, that's us exploiting the design-based structure of the experiment. And knowing randomization makes them all equally likely, and therefore we can count them up and compare them in this way. So now we can take the same logic and say, okay, we have a likelihood of the data of 8 out of 20 from the first population. We have a likelihood of the data from the second population of 6 out of 20. So if these were the only two, we would like the first one better than the second one. Let's go to the last population. 4 compliers, 2 defiers. Could this possibly be what the world looks like? Well, according to the data from the actual experiment, this one does appear to be the most likely because there's just 2 types and they're able to both be balanced pretty well. And so it just makes it true that many different coin flips could have possibly generated this. And so if we're this is the crux of the way that this question is using the structure of the experiment, using these sort of likelihood-based measures to go through what you see in the experimental data, average of y1, average of y0, and then back out what's the most likely population to have generated it. And so that's where it's jumping from marginal distributions from the experiment, which we can measure pretty well, to true distributions, which is the meaning of this paper saying this is like more information. We typically have not used experimental data in this exact way. Okay. So that's why this is the gist of the claim early on, that this is the most likely population, and that's therefore the best guess of the number of defiers. It's based on this likelihood. The likelihood is coming from the design-based structure, which makes every randomization equally likely, and then we're just counting up how many ways could we have observed what we observed, and this population generates the most ways to observe what we observed. And that logic right there, like what is the most likely state of the world to make us observe what we observe, that's the concept that comes from statistical physics for babies, and it is like, physicists call it entropy. Something has a lot of entropy, it is just makes the world very easy. That's a version of reality that makes what we observed relatively common, and that's the exact logic that you're seeing here. Okay, so that was if we are commonly understanding that what the paper is doing and the type of question it's asking, and then the type of method that it's using, and where the distinctions come, then we're doing great. And that I think that comes out really well from the 6-person experiment. We're not asking about treatment effects parameters per se. We're asking about something much more broad than that, which is what's the whole joint distribution of potential outcomes. We're not doing it with a typical kind of estimation identification approach like we normally do. We're doing it with this likelihood-based approach of exploiting the randomization and then counting up like how likely is this population to have generated what we saw. And now we can talk a little bit about what this generally looks like in larger and therefore more realistic sample sizes. So here we're going to go to a figure that is probably going to benefit from more discussion beyond what I say, because I would say this is sort of like the crux of the paper, and it has a lot of information in it. So I'll say the information that I know, and then you should make sure that you get the authors to say the information they know, because it will be a lot more. So imagine that we didn't have just 6 people, we had 50 people, and 25% of them, 25 of them were in the treatment group, and 25 were in the control. And the x-axis of this big figure is going to be how many out of your 25 kind of took up in the treatment, meaning how many quit smoking, how many survived after the treatment, or again, of course, in the IV interpretation, how many complied with the instrument and did the treatment, however you want to think of it. So this is just the in the intervention, you can think of it. And then this is the same thing for the control group. Okay? So every cell on this big grid is one potential experimental result. This one says I did an experiment with 50 people, and 0, 1, 2, 3, 4, 5 people took it up in the treatment group, and 0, 1, 2, 3, 4, 5 people took up in the control. That would be like that box right there. And so each cell on this graph is a potential experimental result that you could have gotten. And you can see just how this would be reported in your experimental table. Control mean is whatever the share is on the y-axis. Treatment effect is x minus y. So now what you can overlay here is a heat map that contains a huge amount of information, but it's all coming from just exactly what we said. Because think about that 6 and 3 example. All we were using there was the share who quit smoking in the treatment group, that was 2/3, and the share who quit smoking in the control group, that was 1/3. And that's all we needed to know, given one guess about the potential outcomes. That's all we needed to know to map that population structure through the randomization to a likelihood. That's what we needed. And so this is all like a much more complicated version of that same thing. What you're seeing in the shading is the likelihood, the number of defiers that are picked by the maximum likelihood method. And so for the 6-person example, that was 2. For here, it could be any number. What you're seeing in the area, so then what you're seeing in the regions that are highlighted here with thick black line is the share, is the part of the experimental results where the treatment effect is positive. So anything where take up count in intervention is greater than take up count in control. This is my 8 is a positive number, and then over here my 8 is a negative number. So that's fine. You could get different experimental results. And what you're seeing in the shading is the places, and what you're seeing in the annotation here is which set of types are in the optimal, in the MLE guess, in the maximum likelihood guess about the population distribution. And the thing that is not worth talking about in the most detail at the moment, but is crucial for understanding what we mean when we say our guess about the population, is that in this setup, just telling you the number of defiers in the experimental results tells you the whole set of types. It tells you all of these things. So once you pin this down and you know the treatment mean and the control mean, you know those things too. So that's why everything is indicated by the shading of just like one of the types, because it fully tells you. And you can kind of think through that in the monotonicity example. If I tell you there are absolutely no defiers, then anybody who doesn't take in the treatment group, so that's pinned down. And you can do you do the same thing. So The important thing here is just to note that there's a lot of information by this logic embedded in what you actually see from the experiment. And so if you see a result where there is a huge take-up count in the control group, so you're way up on the y-axis, and not very many people take up an intervention, that might, according to this method, that indicates there's maybe a lot of these backfiring people because you're in your control group, you didn't give them the treatment, and yet many of them did the thing. And so that just suggests that it's likely that some of them were defiers, and potentially many of them were defiers. And if you want to go to the very extreme where you can be super confident, if you did an experiment and nobody in your treatment group took the thing up, and literally everybody in the control, everybody is a defier. And this is yet another place where I think making the distinction between the IV interpretation of these words and the treatment effect interpretation of these words is very important, because defier is making us think like in IV language, but all that is going to mean is my treatment effect is -1, -100%, and that suggests that the treatment is bad for you, and that's the definition of like a quote-unquote defier when we think of the outcomes. And so you can get a lot of the usual cases if you look at the corner here. The opposite would, of course, be I did an experiment, every single person in the treatment group survived or quit smoking or did the thing I wanted, and literally nobody in the control group did it. That would suggest that everybody is a complier. Nobody does it all the time. Nobody does it never. The only thing is complying. There's a lot more going on here. Another thing that you could imagine doing with an experiment is doing like Fisher's exact test of the sharp null of literally no treatment effect on anybody. And you can see that sharp null on this graph right on the basically 45-degree line. That's the set of cells where the take-up count in treatment equals the take-up count in control, and that's what you would observe with the sharp null, where the treatment literally doesn't do anything for anyone. In a sample size of 50, with 25 in treatment, 25 control, they've also nicely outlined the region where this Fisher exact test will reject that null. But what they're showing here, what you should notice in these regions inside this gray line, which nevertheless the MLE picks out some amount of compliers or defiers, is that that's different information. That's more information than Fisher's test would tend to give you. So another way to say the sharp null is to say everybody is an always taker or a never taker, which means it doesn't matter what you give them. They're not going to do anything. That's the sharp null. But these little triangle things right in the middle are different. They're in an area where Fisher's test would say everybody is an always taker or never taker, and yet the structure of the experiment suggests that there might be some defiers and might be some compliers, and you could still live in this space of the experiment because they could be offsetting each other. And so that's more than we would typically have taken away from a permutation type test. These regions demonstrate like a key subtle advantage of thinking through things this way. So I'm going to allow authors to handle questions about like this rest of here. And the last thing I'm going to say is how I think we should think through what we get out of this method. We're going to get a choice. So like the output of doing this is going to be, I have chosen that the best defier count in the data is 20, 10, or 4, or 7, or something like that. But what's important is when we do that, if you think back to our example with 6 people and 3, the paper shows the likelihood. We showed you 8 out of 20, 6 out of 20, 12 out of 20. The paper shows that likelihood for every number of defiers that you could have. And implicitly in this exercise, all population distributions are treated as equally likely. So one way you could think of it that the paper phrases too is as a totally uninformative prior on the types. That means in some regions, you will for sure always, no matter what, conclude that there are some defiers. And so this is a place where I think extra structure, extra assumptions on the distribution of the population could really help. And it provides a really clear place to bring those assumptions in. So if you were to know institutionally that defying is impossible, like for example, suppose that these were not humans receiving healthcare interventions, they were lab rats that you could keep in cages and you controlled their diet, you would be controlling compliance. And so in fact, I don't think this method would be appropriate in that case because we would have very informed prior on compliance. That's an extreme example, but there are other cases where, suppose an economic model would suggest defying was not optimal or not possible. Suppose the institution said, if I rule you out of this clinical trial for this new drug, there's literally no other way you can get the drug because it's still being tested. That'd be more information on compliance, and that would be something where you could limit some of the regions here, or you could limit the MLE in a certain way. And so I think a key place for the paper to go, which I know they're thinking about, we talked about this last week, is this is a really helpful start in how to use the structure of the experiment to try and go a little deeper. But it can probably do much better by being combined with other ex-ante information that kind of makes the space of things you could choose slightly less wide. So I think this is something that would be fascinating to start with. Just a final thought too, like an interesting thing is, of course, other methods to understand if there's defiers. I tend to think of the paper as already having, let's say, fully conditioned on a bunch of stuff that might be in your causal forest, but it might pair well with methods that look for evidence of treatment effect heterogeneity and sign by observables. And then this would essentially apply within an observable category. And so again, it would pair really well with tools like that.
Thanks, Andrew. That was a super nice discussion. I really appreciated that. I'm going to go ahead and invite Amanda up here since we're both here. And I think we want to probably just start by saying, asking if there are kind of any first order concerns or thoughts that we should address before, thinking about our responses to what Andrew said.
Can I just ask something?
Yeah.
Is it possible for you to go back a couple of slides?
Yes. Tell me when to stop.
This one?
Yeah, this right here.
I was just wondering, so wouldn't a Bayesian look at that and say, okay, the posterior probability someone's a defier equals the prior I have on each of those three possible groups times then the likelihood.
Yes.
And then I'd have to divide by the marginal likelihood of it. So I'm just curious, why are you not doing it that way rather than just looking at the likelihood?
So partially this is a style thing. We wanted to offer something to someone who doesn't want to have to take a Bayesian perspective. In the paper, we actually do take a kind of Bayesian argument. We specifically were proposing this as a decision rule, and we demonstrate that it's optimal for Bayesian with a uniform prior over all of these possible groups here.
Yeah. So if it's a uniform prior, it's the same thing.
Yes.
Right?
Yeah, exactly.
But as Andrew was saying, you might there are cases where you would have strong priors on
Exactly. We think broadly the kind of priors that we try not to be too restrictive on what prior we think you should have because it's going to vary a lot on different cases. What we think is most interesting for the content of the paper is a prior that is specifically uniform over rows that look like this, right? Where you have the same marginal distributions, so the same total number of orange on the left and orange on the right. We think you should be somewhat, probably indifferent between these. You probably don't have any prior information once you've conditioned on the margins. But as Andrew was saying, there are these cases where you can enforce perfect compliance and things like that, where you probably would want to do that. Generally, when you have some sort of non-uniform prior, you can get the kind of optimality result we have by using the maximum a posteriori estimate instead of which is the maximum likelihood in the case of the prior. Yeah.
I have a question. It may be very basic, but I'm wondering, in practice, when you have an intervention for their participants and people that drop out of participating in the control and the treatment, and they are in this assumption, are they by default assume the fires, or because they could be just deciding not to participate, but they may, in the example of smoking and no smoking, they may already say, I do not smoke, so why do I participate and spend my time participating in this intervention, even in the treatment or the control? How does one manage to with this reverse engineering, or what is the real population?
So in this case, the likelihood we've written down is valid kind of only when people aren't dropping out. And I think to make these kinds of likelihood-based decisions in a case with attrition, we'd actually have to like write down a new likelihood. It says one of the types is perhaps someone who quits, or that these are kind of someone who you didn't observe either half of their circle here. So I don't know, we haven't thought about this in depth. I think we would have kind of, based on the kind of logic presented here, we kind of have an idea of how we would approach this, which is like, this is, we'd have to think about it, this is a circle who we didn't get to see either half of.
Do you mind if I jump in with
Yeah,
something?
yeah.
So we use the terminology, always taker, complier, defier, just because we thought people knew that terminology, even though we were really kind of excited about thinking about somebody who'd live regardless, somebody who'd have their life saved, somebody who'd be killed, and somebody who'd die regardless. And that's in a setting where there's just a binary intervention and a binary outcome. So when we're usually talking about always takers, compliers, never takers, and defiers, we actually have 3 variables instead of 2. We have the randomized binary instrument, we have the endogenous variable for take-up, and then we'd have some kind of outcome mortality. But here we're either just doing the first stage of the IV model or the reduced form of the IV model. And your question, I think, is asking about what if we had a full IV model, where there was a first stage with imperfect compliance, and then there was also a second stage outcome mortality. How could we incorporate that? And I think at one point Neil actually did derive the likelihood if there were 3 variables. This was years ago. There's just a lot going on in this paper. So
We haven't looked at that one as in depth as this because we found out that this was really complicated.
Yeah. So I think that you could actually derive the design. I don't think it would be hard to derive the design-based likelihood for having a model that actually is the IV model with 2 stages. And the thing that it could bring you there is you could think about not only violations of monotonicity, but you could also think about violations of the exclusion restriction. And that, I think, amounts to the question that you're asking about, of like, for the person who didn't take it up, was there any impact on the outcome that has to do with the exclusion restriction? I think that would be a really, like, relatively simple extension of this paper, but we just started with something simpler.
Did you think about looking more at partial identification rather than just the maximum likelihood? That's what I would think about as like, you could bound the number of defiers that are consistent with the data that you see. And then that kind of environment's easy to bring in the sample selection issue into the experiment because you could just, expand the worst case bounds depending on all the combinations of what those people who self-selected out of the experiment were gonna do. And I also think kind of related to that is like, if you talk about in the paper, like, what do you do with this information? Like, if you don't know who the defiers actually are, like, there's still some sort of cost-benefit analysis or welfare analysis on whether or not you actually do the treatment. And so then thinking about like what the maximum possible number of defiers could be and whether or not the treatment is still beneficial on net in that situation would be useful.
I want to actually jump. I'm going to answer the second part of that first. Let's see. I forget how far into this is. Is this right?
Yeah, it's this one.
This one. Okay, I have to make sure I say the right thing. Okay, so this question of, you don't actually know who the different types are. This is all statements about the distribution, right? It's not like an individual type. There are certain outcomes that can, if you believe your maximum likelihood distribution as your guess, you can start to conclude certain types for certain people, right? So here we have a couple of examples, and in the second column here, this we're looking at this kind of famous paper on opting in or opting out to be an organ donor. We find here that our maximum likelihood estimate estimates that there's no never takers, and there's positive counts of always takers, compliers, and defiers. And so what this lets you say then is, well, if I see someone who does not take up the intervention in the, or sorry,
I'm the prop.
yeah.
I don't know if you've seen this yet with the cookies. So I didn't take up in control. You don't know what happened to me in intervention. I'm a complier. In this MLA, if there are no never takers and I didn't take up in control and I took up an intervention, I'm a complier. If I didn't take up an intervention, you don't know what happened to me in control. If there are no never takers, now I'm a defier. So this is pretty cool because now there are specific people in the experiment. So normally when you have no defiers, you can't actually tell who the compliers are. You can get their average characteristics. But now there are the specific people in the experiment. If you're under this no never takers assumption, which is a strong assumption, but was informed by our design-based maximum likelihood estimate, you know who some compliers are and you can see them in their average characteristics, and you know who some defiers are and you can see them in their average characteristics. And you could try to use that for targeting. Shout out to my research assistants up in the last row there. We're actively trying to work on doing that in the specific example of Johnson and Goldstein.
Going back to the first half of the question, partial identification. There's like kind of something going on here where, because we have this really design-based view, it's not, we're basically holding the number of people in the sample constant and what their potential outcomes are. And so we've stayed away from talking about identification in this case because we're not really sure what it means. There is, of course, the kind of more standard sampling based, like I have some superpopulation in mind that I drew these people from, and there we would say things that like, yeah, the share of defiers is partially identified. You can establish some bounds on them. What I think is kind of interesting, do we have the extended table?
Oh, I don't think we put these in the table.
We don't? Okay, that's fine. No, it's fine.
Oh, that's too bad.
You can kind of have, if you start with this partial identification view, you can kind of make an estimate of what those bounds would be in your sample of like, I think there's somewhere, the bound suggests that there's between, 0 and, I'm trying to think what it is for one of these.
Here, the bounds on defiers would go from 0 to 18%. That would be the upper
Oh yeah,
Fauché
right, of
bound.
course, right.
The upper Fauché bound would be 18%, which would occur if everybody who didn't take it up in the intervention group was a defier. So we are getting the upper Fauché bound here. Sorry to...
No, that's great. That's what I was trying to say. This is nice because it kind of lets us say, at least when we're restricted to our sample, we do have some information in our sample that is like within that partially identified set, which is kind of counterintuitive. Yeah.
And as a clarifying question, the Fréchet set is all the joint likelihoods, all the joint outcomes that have a likelihood greater than 0.
So what let me go back a few slides here. We used Fréchet set to mean something really specific in this paper, where we're saying that there is, for any two for any set of two marginal distributions of potential outcome in intervention and the potential outcome in control, we kind of think of the Fréchet set as all the distributions with those marginals, right? So for instance, in this 6-person example, this is a Fréchet set. This is all of the possible arrangements of 6 people such that 4 of them are orange on the left and 2 of them are orange on the right. And kind of, I think that what is kind of the big novelty that we're trying to exploit here is that in a superpopulation, it's kind of well understood that you can't really learn within this set, right? You can learn across these sorts of Fréchet sets, but you don't really gain any information about where within the set you are. Turns out when you condition on the sample, there is some information there.
And the information you're getting is the likelihood. Yes, you're conditioning that you know the marginal distributions.
When we do the full maximum likelihood approach, we actually we allow it to, you know, essentially also tell you what, you know, because there are basically places like where the Fisher's exact test doesn't reject and things like that, where the most likely thing is actually not what is perfectly aligned with the estimates of the marginal distributions that you get. It just, you know, turns out that it's more likely that those were kind of flukes. We can also do the kind of exercise you're suggesting, which is saying, okay, let's say we're relatively confident that we're in this Frichet set. Now let's kind of condition on that and look across the various distributions there.
Okay, well, as we are done